Okay, it's the last wee video on work and energy, and it's moving into power. And power is the rate at which work is done. And we say that at 1 watt is a unit of power. 1 watt is the rate of working at 1 joule per second. So it's the work done divided by time. But also you can see work done per second is force times distance moved per second. So force times distance is work done, and if we think of that per second and just move that out slightly differently, that's force times distance moved per second, which is force times velocity. So we also see, as well as work divided by time, it's also force times velocity. So a number of examples here just to deal with power. The first one, a car of mass 800 kilograms, driven along a level road with constant resistance of 450 newtons. So we have the engine of the car providing a force forwards and resistances of 450 newtons backwards. We do have the weight of the car, 800g, and normal reaction as well, although they'll not play any part in this question. It was good to put those forces on it. We're told the output of the engine, or the power of the engine, is 7 kilowatts. Find the acceleration of the car when the speed is 10 meters per second. Okay, well, when it's 10 meters per second, it's accelerating here. We want to find that acceleration. And overall, you can see then, just using F equals ma, that x minus 450 is equal to the mass, which is 800 times the acceleration. And we want to find this value x. What is that force? And this is where the power comes into. We know that the power is force times velocity. And in this case, we know the power is 7,000 watts, 7 kilowatts. And that's equal to that force x times the velocity, which is 10 to 10x. And so we see that x is 700 newtons. And when we plug that back into our Newton's second law, we see that 350 is equal to 800a. And when we divide that, we get a to be 0.315 meters per second squared. Now the second part of this question then says, okay, find the maximum speed of the car. And when it's at its maximum speed, it can't get any quicker. Its acceleration is equal to 0. So when it's equal to 0, you see the force x must equal 450 newtons. So x minus 450 equals 0 if you put it into Newton's second law, where x equals 450. And then again, we know that power is force times velocity. Now the power output of the engine is 7 kilowatts. That's not going to change. So it's still 7,000, but this time the force is 450. And we want to find the velocity. So divide that through, we get v equal to be 15.6 meters per second. The second example, slightly different. The car's moving up a hill at 10 degrees to the horizontal against constant resistance of 250 newtons. Its maximum speed is 45 kilometers per hour. So let's put in what we know here. We've got this 900g. We've got a resistance of 250 newtons. It does have a normal reaction, as always. And again, we've got the engine providing that force x up. This is 10 degrees here. Okay. Its maximum speed is 45 kilometers per hour. So again, at maximum speed, a equals 0. So if we look parallel to the slope, then you can see that x minus 250 minus, don't forget about this is 10 degrees in here, so that's 900g sine 10 is equal to the mass times the acceleration. Well, the acceleration is 0, so that's just equal to 0. Now, when we put that into our calculator, we know 250, we can work this out in a calculator. We get our value of x then to be 1,781.6 newtons. Now, again, we know that its maximum speed is 45, but just be careful here. It's 45 kilometers per hour. We're working with meters per second. So quick recalculation here. 45 kilometers per hour is 45,000 meters in 3,600 seconds. And that works out then at being 12.5 meters in 1 second. So 12.5 meters per second is our maximum velocity, or maximum speed. So if we then put that into our power formula, P is equal to F times V. We want to find this power output. It's the force, which we've got is 1,781.6, multiplied by this maximum velocity, so 12.5. And that power then is roughly 22.3 kilowatts, 22,300 kilowatts. Again, the three significant figures, I've just rounded that. Second part then of this question, find the initial acceleration when it reaches the top of the hill. So as it goes up the hill, this is all in play, but once it gets to the top of the hill, it flattens out, and we have this scenario here. We have the force of the engine. We still have these resistances of 250, but now the weight is acting perpendicular to the slope, and we have a normal reaction there. Find the initial acceleration when it reaches the top hill. Okay, at the initially, its power output and its velocity is the same, so it's going 12.5 meters per second. We know its power output is 22.3 kilowatts. And again, we can use Newton's second law here, F equals ma. So the force here, x minus 250. Well, that value of x we've worked out is 1,781.6 minus 250 is equal to the mass, which is 900, times a. Okay, the weight now does not play any part of this as it did before. And just rearranging that around, we get that a is equal to, I think it's 1.7 meters per second squared.